Good morning to all. In this class, we are going to discuss about multi-core processors. That is, using more than one processor in a single core, it is called to be multi-core processor. Before going to see what is multi-core processor, we can see about what is single core processor. So this is the architecture for single core computer. The single core computer, it consists of many things. That is CPU chip, which we are calling as processor or chip or core. Here we are having several components. The main functional units of the computer is I/O module, that is we will be having input unit, output unit, CPU or core, then main memory unit, then control unit. In order to control all the units, that is all the functional units, we are using control unit. Control unit will act as a master, whereas for that control unit, your CPU, that is core, will act as a slave, that is worker. Here, in order to connect the CPU chip with other things, we are using system bus. Bus is nothing but set of interconnection wires used for communication. Under system bus, we are having several categories such as data bus, control bus, address bus, like that. To control that one, we are using control unit. Our I/O bus, it is used to connect our I/O controllers. That is input controller, output controller, anything can be connected with the help of I/O bus. So here we are having USB controller. With respect to I/O controllers, we are using USB controller, graphics adapter, as well as disk controller. The main parts of CPU chip are registers as well as ALU. Registers we are used for storing, whereas ALU we are used to perform arithmetic and logical operations. So this is the single core computer. Our chip, single core chip, it consists of register file as well as ALU. Here, when considering this single core chip, if we are using this one in a single system in essence, we are calling that one as a uniprocessor system. Whereas, if we are embedding more than one core in a single chip, single integrated circuit die, we are calling this one as a multi-core processor chip. Here, this multi-core processor chip, why we are using this? Why we are preferring from single core to multi-core in the sense that we are going to discuss in this class in depth. What is multi-core processor? It is a single computing component which consists of many independent components. All the independent components will going to work for you. All the works. What are the works we are going to provide here in the sense? The normal CPU instructions. Either it can be an add instruction, move data, or branch instruction. Anything can be given to your single core when it is embedded into a single chip. It can be used as a multi-chip or multi-core processor. Here, you can embed multiple cores on a single chip, and so we are going to execute multiple instructions parallelly. That we are going to implement it in order to increase the speed of our programs. That is, whatever application we are using, we are going to implement the application with the help of the multi-core architecture. Nowadays, manufacturers, what they are preferring in the sense, they are going to integrate all the cores on a single chip. That chip we are calling as CMP, which is nothing but chip multiprocessors, right? This is an example, a real-time example. This is a single core highway. This one is quad-core expressway. This we can consider as a unique processor, that is single processor, and this can be considered to be a multiprocessor. What is the difference here in the sense? Here you can execute only one program at a time. One program can be executed at a time in a single processor. Likewise, one vehicle can enter the single core highway. One by one it has to enter, so it will take some more time. When compared to quad-core expressway, here what we can do, we can send the vehicles parallelly. Likewise, in our using our multi-core processor, we can execute the programs parallelly in order to achieve speed, so that execution time is reduced. This is the main thing, that is everything, all the cores is embedded. They are embedded in a single socket. So we are calling this one as a single processor socket, otherwise called as chip multiprocessor, CMP. What are these? If we are embedding two processors, two cores in a single die in the sense, we are calling that one as dual core. Whereas if we are embedding four cores in a single IC chip in the sense, we are calling that one as quad core. If 6 cores are embedded in a single IC we are using in our day-to-day life for real-time applications. For solving many real-time applications, we are preferring these multi-core processors. So here, in each core, we are executing our real-time applications. We are real-time applications in the sense our programs. Each program will be executed inside the operating system, inside the computer system as threads. So the first core, it is executing one process in the sense that is considered to be a thread. This is the second thread, that is core 2. Core 3 is executing a third thread and so on. Similarly here, in our multi-core processor, what is the main concept in the sense? We are going to execute several threads inside a single core. What we are calling as multi-threaded programming. So, with the help of multi-core processors, we are achieving multi-threaded applications. We are achieving multi-threaded programming. That is illustrated in this diagram. What does the operating system do for us? Operating system, what it will do now? It will consider each core as a separate processor. So, what will happen? Automatically, the operating system scheduler, it will process, it will map the threads or processes, whatever we are supplying as application programs, to different cores. So, if 4 cores are used in the sense, your programs will be get splitted. It will be executed as process as well as threads, and the threads will be supplied to each and every core equally, so that our applications will be executed soon. That is illustrated here. While we are in single core architecture, that is single core processor itself, we are having everything. That is all the functional units we are having. For providing the input, we are having input module. For getting the output, we are using output module. And for storing everything, we are using main memory module. What is the main difference between main memory and secondary memory in the sense? We will be storing all our data. That is, our program during execution must be present inside the main memory during execution. At other times, it can be present in the secondary memory. So, main memory we are having separate locations. Using the addresses, we can access the data present in those locations. So, main memory is there, control unit is there to control everything. CPU, the main part of the computer, that is brain of the computer, is used for processing your programs. ALU is there for executing the arithmetic and logical instructions, everything. So, all the things are there in single core architecture and single core processor. Then what is the need for us to move for multi-core architecture? In a single core architecture, when we increase the clock cycle, the speed will increase. If we are increasing the clock cycles, the speed will increase. Using single core itself, we can increase the clock cycles and we can achieve the speed. But it is up to a certain limit. If we are increasing the clock cycles to a maximum, what will happen in the sense? Two drawbacks will come into exist. What are they in the sense? One is heat dissipation. At certain time, when we are increasing the clock cycles, heat dissipation, we can achieve the speed, but heat dissipation will be more and efficiency will be decreased. In order to overcome these two drawbacks, and for the real-time applications what we are using today, like climate modeling, drug discovery, protein folding, DNA analysis, for all these things, for data analytics, for all these things, we are preferring more computational power. In order to achieve that computational power and to reduce these two problems, the first one is heat dissipation, the second one is efficiency decrease. In order to overcome these two drawbacks and to use more computational power, we are moving from single core architecture to multi-core architecture, that is multi-core processor. What are the other drawbacks here in the sense? Heat problems, then we are having certain speed of light problems we will be having. Difficulty in design and verification. In single core we are using, in the sense, if we are using one single core, in the sense, we will be having design and verification problems, and large design things we are in need of. Server farms need expensive air conditioning. In order to overcome all these drawbacks, we are moving from single core to multi-core processor. That is illustrated here. Here we are shifting our trends, we are shifting our needs towards parallelism. In order to achieve the instruction level parallelism and exploit thread level parallelism, we are moving from single core processor to multi-core processor. So here in multi-core processor, we are preferring referring two main systems. What are they in the sense? SIMD and MIMD. SIMD is single instruction multiple data stream. MIMD is multiple instruction and multiple data streams. We are preferring SIMD for modern graphics cards. Actually, we are having four classification under lines. Those things are SIMD, that is single instruction, single data stream, single instruction, multiple data stream, multiple instruction, single data stream, and multiple instruction, multiple data stream. The first thing, that is SISD, we are preferring in our normal architecture, Von Neumann architecture. We had seen what is single core architecture, no? That architecture. That is Von Neumann architecture, what we are using for uniprocessor systems. So the third one, MISD, there is multiple instruction stream and single data stream. It is still today it is not implemented. So for our multi-core processors, we are preferring SIMD and MIMD. We are going to concentrate about SIMD and MIMD. If you are using the best example, we had seen no SIMD, single instruction multiple data stream. The best example for SIMD is vector processors and graphics processing unit. Vector processor, if you are using in the sense, we need to use special characteristics of vector processor. Then only it will be implemented well. So in order to know the characteristics of vector processor, what are they in the sense? Vector registers we need to prefer to store our data. What is the main thing in vector processor is, your vector processor is going to use the data of vectors. Vectors, it is going to process array of vectors of data, whereas our normal processor, it will process scalars only. Here, since we are processing arrays or vectors of data, we need to use all these characteristics of vector processor. That is vector register we need to use, vector instructions we need to use, vectorized and pipeline functional units we need to use. What for in the sense? In order to achieve pipelining. That is executing more than one instruction parallelly using a pipeline path. In two-stage pipelining, what are the stages in this sense? Fetch and execute. Regarding four-stage pipelining, we will be using fetch, decode, execute and store. In five-stage pipelining, that is what we are using in our MIPS architecture is, you will be using fetch, decode, execute, write back, mem and write back. These are the 5 stages in 5-stage pipelining. So in using vector processor, we have to prefer vectorized and pipeline functional units. And fourth one, here it's a specialized memory, interleaved memory we are preferring. Here we can gather banks of data together and you can access the data in banks, so that the time can be saved in using interleaved memory. The final one is strided memory access and hardware scatter gathered together. You can access multiple data as input, you can process the data as multiple, then you can receive the output as multiple. That is a specialty in the fifth one, that is scatter gathered together. These are the things under vector processor. Again, GPU, graphics processing unit. It is also a best example for SIMD. Graphics processing unit, it is capable of processing more number of graphics, whatever things we are using under graphics. If we are using polygons, it is capable of processing 10 million polygons per second. So that is the best example for SIMD. Next, we have to see about MIMD. MIMD, multiple instruction, multiple data. So what here we are doing in this is, we are going to process. It is supporting, this MIMD system is supporting multiple simultaneous instruction streams that should be operated on multiple data streams. Example for MIMD system. Here, MIMD systems, they will be having their own control unit, own ALU. Each and every processor will have its own ALU and own control unit. Best example for MIMD system, we are preferring two categories. One is shared memory multiprocessor system, multi-core processor. Two things we are having, two categories. One is shared memory systems and the second one is distributed memory system. So what are the main differences between the shared memory systems and distributed memory systems? We are going to see here. This first category is shared memory system. Here we are going to use more than one processor. That is more than one core, more than one CPU chip. But All the CPU cores will be connected to a common memory. Here memory refers to main memory, common memory. It will be having, each and every processor will be having individual cache memory. But main memory is common to all the CPU, that is all the cores, all the CPU chips. How we are connecting all the CPU chips with main memory in the sense with the help of interconnect networks, right? This is the major thing. Here how communication takes place. How communication takes place here in shared memory systems in the sense, since all the cores are connected with a common memory, communication will be achieved with the help of memory itself. We can make the communication using the common memory. Common memory in the sense main memory itself. Here we are having two categories in shared memory systems. One is uniform memory access and another one is non-uniform memory access. In uniform memory access, what is the thing in the sense? The time to access any of the memory locations will be same for all the cores. That is uniform memory access. Whereas the second category, non-uniform memory access, the memory location that a core is directly connected can be accessed faster when compared to the chip that is located farther, right? Near can be accessed soon and far can be accessed later. This is non-uniform memory access and the shared memory systems. Next comes distributed memory system. Here what is the main principle in the sense? Here we will be having each and every core, that is CPU chip, will be having its own memory. Own memory in the sense, here we are meaning the main memory. So all the cores again will be connected with the help of interconnect. We are next going to discuss about interconnect networks. Here, since we are having individual memory in each and every core, how the communication is going to take place in the sense, with the help of message passing, that is inter-process communication we need. Whereas in shared memory system, there is no need for message passing. Here, since we are using individual memory in each and every CPU core, we are in need of message passing. Next one, OpenMP, it is a programming used for shared memory. That we have seen, we are going to communicate with the help of common memory. For that, we are using a model called OpenMP. It stands for OpenMP model. OpenMP stands for Open Multiprocessing. What for it? It is an API, application programming interface used for shared memory, that to parallel programming. With the help of OpenMP, here we are going to achieve the parallel programming in shared memory systems. Here MP stands for multiprocessing. It is designed. We are going to execute all the processes considering the processes threads. In order to process the threads, in order to achieve multi-threaded programming, here we are using OpenMP parallel programming. Here we are having several library routines. We had several libraries inside this. Using the library routines, we can execute normal communication routines. We can create and we can implement it for multi-threaded application. That OpenMP, that is Open Multiprocessing API, it is using an execution model which uses 4 join parallelism. We know the master thread, it is used to handle all the slave threads, that is worker threads. It will spawn a team of threads for a particular work and that work will be given to the slave threads, that is worker threads. After finishing the work, the slave threads, they will join all the things, all the outputs and they will return it to the master thread. This is called as 4 join parallelism. This 4 join parallelism is used in OpenMP execution model. All these things we are preferring for shared memory parallel programming. Then what about the distributed memory parallel programming in the sense? We are going to use one more API called Message Passing Interface, MPI, Message Passing Interface for distributed memory parallel programming. In order to achieve parallel programming for distributed memory, we are preferring this MPI. MPI is an industrial standard, right? Here we are going to have, here also we are having certain library routines. Using those library routines, we are going to write message passing programs, that is MP. What for we are preferring? Since we are having individual memory, we need to have message passing. In order to achieve message passing, we are going for this MPI, API. Right? API is application programming interface. This is an API, best example for distributed memory. Here, this allows the development of scalable portable message passing program. You can extend it to any number of applications, this API. What are the special applications we are using for multicore in the sense? All these things. Database servers, they are preferring multicore. Web servers for web commerce applications. Then compilers, multimedia applications, scientific applications, CAD/CAM, all these things. What for in the sense? In order to achieve thread level parallelism and instruction level parallelism, we are preferring multi-core processors for all these types of applications. Next, we have seen we are connecting in shared memory systems and distributed memory systems. All the cores are connected with the main memory with the help of interconnect. What is that interconnect in the sense? It is a network. Similar to system bus. In normal 1-to-1 architecture, we are using system bus for connection, interconnection. Similarly, here we are using interconnect. Interconnect networks, it plays a vital role in both shared memory systems as well as distributed memory systems. Here we are having shared memory interconnect separately and distributed memory interconnect separately. Interconnects, they are nothing but interconnection networks used for making communication in between the CPU cores in both shared memory as well as distributed memory. So we are first thing we are using bus interconnect, which is similar to buses. We are going to connect all the components with the help of buses. This will be okay, but if we increase the number of processors, then bus creates contention. So what happens automatically in the sense the performance will decrease. If we are using the buses for interconnection, if there's more number of processors are connected in the sense, contention increase and therefore performance will decrease. In order to overcome this drawback, what we are doing now, we are moving to the next interconnect called switched interconnect. How the switched interconnect are implemented in the sense, with the help of cross bars, we are implementing this switched interconnect. Here, there is no need for us to worry about contention. What will happen now? Here, simultaneous communication will be achieved among different processors with the help of switched interconnect. See, this is faster than buses. When compared to buses, this is faster, but the cost is high when compared to buses. This is the diagram for interconnector. There is shared memory. We are using crossbars. There we are using processors, and this side we are using memory. M1, M2, M3, M4 are memory, whereas P1, P2, P3, P4 are processor. Memory, it is going to have communication with processor. The second diagram, here we will be having the first thing, the thing is no memory access takes place. If the switch is like this closed in the sense, no memory access takes place. Whereas in the second, we are having that is memory access. Memory access in the sense either memory read or memory write may take place. So here in this third diagram, what is illustrated is memory M1 is communicating with P3, that is processor 3. In the second case, M2 is communicating with P4. Then third case, M3 is communicating with P2, and in the fourth case, M4 is communicating with P4. The communication in the sense either memory access, that is memory read or memory write takes place. This is the first category of interconnect. Second one is distributed memory interconnect. So far we have discussed about shared memory. In distributed memory interconnect, we are having two categories, direct interconnect and indirect interconnect. In direct interconnect, each switch is directly connected to a processor. Whereas in indirect, it is not possible. That is, switches are not directly connected. We will be having a processing network with incoming and outgoing links in indirect interconnect network. So we are going to see about a direct interconnect. Ring, toroidal mesh and hypercube. They are the best examples for distributed direct interconnect. So here each and everything we will be having in P1 we will be having SPM, that is switch, processor and memory. Everything will be there in each processor, and all those things are directly connected with each other in ring as well as toroidal mesh. Here the links required is less when compared to toroidal mesh. Toroidal mesh will be having more number of links. We will be requiring more number of links in order to achieve communication. The next one is hypercube. In hypercube, we will be having three cases: one-dimensional hypercube, two-dimensional, and three-dimensional. Two-dimensional you will be building with the help of two one-dimensional, and three-dimensional you will be having two-dimensional. Here also the links required are more, but communication is achieved faster when compared to the remaining things. These things are examples for indirect interconnects. Last one is direct interconnects. Next one is indirect network. Indirect network will be not connecting everything with the switches directly. Here you will be having switching network. You will be having one incoming link and you will be having the outgoing link. So since it is not directly connected to the switches, we are calling this one as indirect interconnect. Right? Previously, everything will be connected directly to the switches, so we are calling that one as direct interconnect. Here it is not directly connected, so we are calling these types of interconnect as indirect interconnect. This is the example for crossbar. Here what will be having? We will be having incoming link and outgoing link. So communication may take place with the help of incoming and outgoing, with the help of switching network, not switches alone. With the help of switching network, communication is taking place. In crossbar, this is the example for omega network. Here also the same principle, incoming and outgoing with the help of a switching network. Next comes performance issues. We had seen so far, we had seen about multi-core processors. And what are the categories in that? What are the systems we are using? SIMD, MIMD we are using. What are the performance issues in multi-core processors? In the sense, several things we are considering here regarding performance. First one is speed up. What is speed up here? Number of cores we are using is P in the sense. What we will do? We will divide our work equally among all the processors. So, serial runtime. If you are having a particular application, you are supplying the application program to your multi-core processor in the sense. See, what about the serial runtime? That is when it is executed serially. That is considered as serial runtime, T serial. Parallel runtime is T parallel. So, T parallel, linear speedup. The formula for linear speedup is T parallel is equal to T serial by P. P is nothing but total number of processors or cores. So here speed up can be defined as parallel, T parallel execution time, serial execution time divided by parallel execution time. That is our speed up. That is formula for speed up of a parallel program. That is, if you are running your program parallelly in multi-core processor, the speed up can be calculated with the help of the formula total execution time for serial divided by parallel. So what about the efficiency of a parallel program? In the sense, efficiency is equal to speed up, what we had defined already, divided by P. P is nothing but number of processors. So T serial by T parallel, already we had defined for speed up, divided by total number of processor P will give you the formula for efficiency. This is the second performance measure. So first is speed up, second one we are considering efficiency. This is the curve for speed up. It is increasing with the help, when the number of processes is increasing, it is increasing. Whereas efficiency, it is decreasing when increasing the number of processes. Here, effect of overhead we need to consider. For the large applications, whenever we are calculating the parallel runtime, we will be calculating this overhead also. So it is additionally added, right? The last parameter, Amdahl's law we are considering. What it is telling, what is Amdahl's law is telling in the sense, we need to parallelize the entire program. If you are parallelizing only a small amount in the sense, that much performance alone we can achieve. If you are parallelizing the entire program, the entire application in the sense, we can achieve good performance and speed can be increased. That is illustrated here. So here a small example. I am parallelizing 90% of my program in the sense, what will happen? 90%, the runtime of parallelizable part can be considered to be 0.9. T serial is given 20 seconds. So you will be multiplying with that. 0.9 into T serial by P will give you 18 by P. This is parallelizable part. What about non-parallelizable part in the sense? 90% is parallelized. So remaining 10% is unparallelized. So we need to consider that 0.1 into T serial is equal to 2. So here we are going to overall parallel runtime, how will you achieve? we have to add both parallelizable part and unparallelizable part. So we are adding these two things, right? Finally, we are calculating, yes, speed up. It is nothing but T serial by T parallel, already we had discussed. So 20 divided by 18 by P plus 2, right? These are the things regarding performance, 4 things. We are concentrating on speed up, right? Speed up, next to that we are concentrating efficiency, then Amdahl's law. Last we are having scalability, that is how we can tell that your system or your processor is scalable in the sense it should handle any number of problem size. If it is handling big number of problem size in the sense, we can tell that it is capable of handling the scalability, right? Here we are having 2 categories under scalability, strongly scalable and weakly scalable. What is strongly scalable in the sense? If we increase the number of processors in multi-core processor and keeping the efficiency fixed without increasing the problem size, we are calling that one as strongly scalable. Whereas weakly scalable, if we are keeping the efficiency fixed by increasing the problem size at the same rate as we increase the number of processors, the problem is said to be weakly scalable. These are the 2 things regarding scalability. Then as a last step, we are having 4 steps in parallel program design. What are they in the sense? Whenever we are designing our parallel programs, in order to use multi-core processor, we need to use 4 steps. What are they in the sense? As the first thing, here we are using a methodology called Foster's methodology for parallel program design. What are the steps in the sense? First step is partitioning. What you need to do in partitioning in the sense, you have to divide the computation, what you need to compute, into several number of steps, small tasks. That is, dividing a big task into several small tasks. Here you need to identify the tasks which can be executed in parallel. This is the first step in Foster's methodology for parallel program design. As a second step, we are using communication. That is, we are going to determine, we have identified small tasks. We have to make the small tasks to communicate with each other. That is the second step in Foster's methodology. That is determining what communication needs to be carried out in between the identified tasks. And the third step is agglomeration or aggregation. That is combining the tasks and communications identified in the previous step into larger tasks. That is agglomeration, right? Here, if a task A must be executed before task B, what you need to do? You need to consider that one. We need to execute task A first, then task B should be executed. We need to identify that one in this third step of agglomeration. And as a last step, mapping should be done. That is, we had identified small tasks, we had combined that one into larger tasks using communication. We need to assign the larger tasks to your processors as threads, right? That is the last step, mapping. Assigning the composite task identified in the previous step to process or threads. After that one, what we will do, we will assign all the process, all these large tasks to individual processor, and the processor will take care of all the processing and it will return the results to us. So far in this class, we had discussed what is multi-core processor, what is multi-core architecture, why we are moving from single-core architecture to multi-core processor or multi-core architecture, what are the categories in the under Flynn's classification, and what are the things we are using for multi-core processor. That is, SIMD and MIMD systems we are preferring for multi-core processor. What are the examples for SIMD systems? That is, vector processors and GPU are examples for SIMD. And what are the examples? What are the categories under MIMD? MIMD, we are having 2 classifications, shared memory systems and distributed memory systems. What is the difference between these 2 things that we had discussed? How we are connecting all the components in shared memory systems and distributed memory systems. That is interconnects. What are the types of interconnects we had discussed? What are the performance issues in multi-core processor that we had discussed? Then at last, we had seen the steps for parallel program design, which we used Foster's methodology. Thank you.